Okay, guys, we are live on YouTube right now. So essentially, I guess we can start. Rishi,
Yep.
would you like to start?
Yeah, sure. Okay. So, good evening, everyone present here. So, this is our 10th lecture, as you all know. So, it's been a fun journey from the beginning to the end. And we've kind of changed things up a little bit today because using this new parsec technology, we can now collaborate with one or even more speakers. So okay, so the paper, we'll be talking mostly about the paper in front of us right now. So as you can see here, a pictorial introduction to differential geometry leading to Maxwell's equations as three pictures. So what we are trying to focus on this paper is not the mathematical aspect of differential geometry. When you hear me say that, you all be like, wait, but then differential geometry is just math, right? It's like differential operators and like integrals and exterior differential forms and blah blah blah. But then this paper, that is why we found this paper so interesting, because this paper had literally zero mathematics in it, and I'm not exaggerating here. You will find zero equations and literally zero derivations. So when I first read this paper, and then me and Pugazharasu read this paper, we were like, you know what, we should do a talk on this, because this provides a pretty consistent and pretty good base for what people can take forward if they want to study differential geometry. So we are three speakers here today: me, Sundaram, and Pugal. So I'll be handing the session over to Sundaram in a while. But then before we get started with this, I want to make, like, let's say, a small disclaimer, right? This talk or this lecture isn't a comprehensive lecture, or else it doesn't cover everything in differential geometry, because you'll be a fool to think so. What this paper tries to do, at least, it doesn't completely, um, what do you call it? Doesn't completely succeed or so, but then it tries. He's the writer has tried quite a bit to visualize differential geometry. So, putting forth that disclaimer, I would also like to make the point that if you in any way feel lost, or you feel confused in what this is or what the diagrams are, you know don't feel hesitant to ask us any questions, or please stick till the end, because sometimes you might get stuck in the first section, but then I or Pugal might clear it up later on. And I hand the session over to Sundaram. Sundaram, you have the mic.
Thank you, Rishi. So yeah, good evening to everyone here. My name is Sundaram, and I'll just start off right away right here. Okay, so we can see that differential geometry is like it's actually supposed to be a very useful tool in physics and mathematics, and it's quite a technical side of things, because it handles three areas. I would say it's a combination of three areas rather: analysis, geometry, and of course, um, algebra. Yeah. So when all these three come together, analysis is just a fancy word for calculus, if you're wondering. So yeah. So once you have that, like all these three come together, and you can represent a lot of things. But right now we're not going to be going that deep into that. Like, just like Rishi said earlier, I would also like to put in the terms the disclaimer he gave, that you can't expect to understand all of it in just one day. It's not like just go through it and you'll get everything right there. So yeah, like Well, yeah. Okay. Uh, can't hear me. Wait. Am I audible now?
Yeah, now you're audible. You kind of stopped working like 2 minutes ago. Go ahead.
Okay. Okay. Yeah. Yes. So yeah. As I was saying earlier, different. I like to further, acclaim the disclaimer that Rishi gave, that we can't understand differential geometry right as we are going into it. So this paper is rather about looking at things, understanding them, and absorbing that for future purposes, or like when we actually deal with differential geometry. So yeah, as we can see, differential geometry is applicable in both physics and mathematics, and in the context of physics, they are applicable for these few points, like three-dimensional space of Newtonian physics, four-dimensional space time of special and general relativity, two-dimensional shapes like spheres and tori, six-dimensional phase in Newtonian mechanics, seven-dimensional phase time in general relativity, the state space in thermodynamics, so on and so forth. Yeah, all these are applicable things, but like it's often used for general relativity. If I'm being quite honest, and if I remember right, Chinmaya was dealing with this earlier, like on his earlier Sunday session. Yeah. So you could go with multiple dimensions into this, like is just geometry, and it's just applicable on all those things. So right here we will refer to exterior differential forms as forms, and they're found in both of those. Electromagnetism, you could use it to define electromagnetic fields, or you could even use them as objects that can be integrated in mathematics. But we'll stick more to the physics side of this. And yeah, right here we have the metric is quite important to define differential geometry, because many like it's mentioned right here, you wouldn't understand it entirely as long as you get into it. Otherwise, you might as well call it differential topology. So you could think of a manifold, which I'll get to a little later. As it's made of rubber, it's infinitely deformable. But if you have a metric, which is basically something that measures the angle between two vectors and vector length, you would have that. You could understand that. But however, it's also like why aren't we learning with a metric right here? Like, why aren't we getting too much into the mathematical part? Like it's mentioned here, there's a lot of reasons here. And I also told you earlier, we would have to learn things like capture. The whole goal is to read stuff, look at the images, whatever, and capture them, and understand them, have a sense of intuition when we do this. Another reason is that you could construct a manifold on any form, and it could like you could construct it on any metric, and doesn't have a single preferred metric, or like not one with a physical significance. Like you could put a manifold in any form. So yeah, like an example is right here. Phase space does not possess a metric, and neither do natural manifolds which study differential equations. So yeah, in order to you would also need like the stress energy momentum tensor for in order to derive Einstein's equations. You have all those examples. So before we dive into it, we try to understand the things before we actually go into it. So yeah, that's one thing that I'm going to make clear right here. And yeah, when we can also depict Maxwell equations with this, and pictorially represent electromagnetism and electrodynamics. But the problem with Maxwell equations right here is mentioned. They are represented on four-dimensional space-time, and we don't have four-dimensional paper, of course. I mean, quite honestly, paper is viewed in a very layman way as two-dimensional, but it actually has three dimensions, but you actually can't represent three dimensions there. But yeah, you get the picture. So even if we were blessed with four-dimensional paper, there would be five spatial dimensions, and therefore six-dimensional space-time. So you could keep going on, and there's always going to be a challenge with Maxwell equations. But like I said, we'll not go too much into the physics right now. Rather, we'll just be viewing the images and try to get the intuition we would need when we are handling the physics part of this. All right. So getting into what manifolds are, manifolds are like, very fundamental objects in differential geometry. There are a number of complex ways to explain this, but we could just look at a manifold, and in a very intuitive way, we could say, if we zoom into a manifold, like we do right here, a patch of a sphere, if we keep zooming in, we notice that the patch keeps getting, flatter, like, the poles or anything as such. Like, you could visualize the Earth or anything. You'd often notice that in the map of the Earth, they would show the North Pole and South Pole as flat. So, you can view the Earth as a manifold because, you can always represent it in a flat manner. There's a more complicated, there are more complicated definitions with respect to Euclidean spaces and other stuff, but, we will stay out of that and rather focus more on the images. So, yeah. You have examples of manifolds right here. A point has 0 dimensions. A curve has 1 dimension. A surface has 2 dimensions. You get the picture. 3 dimensions for a volume and blah, blah, blah. Okay. So if I had to represent this, like, you could keep going. You could keep dissecting these images, and you'd often get a flat point. Like, in a curve, you keep zooming in, you would get a flat point at some point, right? So yeah, you have a manifold right there. And even here, while this doesn't look too, just keep zooming in and you'll find what you're looking for. Like, it's going to be a flat surface. But versus this, a corner. So if we keep zooming inside this, we often notice that we're just reaching another corner, and keep noticing that it's actually a corner, not something you could flatten out. So that's not a manifold. So yeah, getting right into what a submanifold is. A submanifold is a manifold contained inside a larger manifold. It's just like a manifold within a manifold. So yeah, an embedding manifold. That's another way to call it right here. So yeah, the submanifold can either be the same dimension as the manifold it is in, or it could be a different dimension altogether. Different dimension altogether in the sense there's a limitation. It can't go higher than the same dimension or the lower dimension. Like, it can't go on a higher dimension than, because that's sticking to realism, that's not possible. So yeah, right here I can show you some examples. Here's a submanifold right here within a one-dimensional manifold, and yeah, this is another two-dimensional manifold. Right here, so on and so forth. There's a tori within a three-dimensional manifold and a sphere within a three-dimensional manifold. And yeah, getting to what compact and non-compact folds are. In embedded manifolds, there's often boundaries. When they're limited by boundaries, there are they're compact. Like this one, for instance, this one is compact because it's surrounded by boundaries right here. But a non-compact manifold like this one you see right here stretches up to infinity, or like whatever is the limit right here of the manifold it is within. Just think of this as shapes. I know manifold and submanifold seem like very fancy terms, but they're just simple shapes. Just make sure that you can define a manifold as something that if you zoom into it, you get a flat surface as such. All right. So next we'll be looking at scalar fields. What are scalar fields right there? So once you have a manifold, the simplest thing you can define are scalar fields. And yeah, you could define them simply as real numbers associated with each point. So like if wait, let me find the right item. Yeah, if I have a point right here, like this one, for instance, there's a point right here, there's another point right here. So yeah, each are represented by real numbers. So yeah, intermediate values and some of the values. Yeah. So that's one way of looking at that. And yeah, wait, let me go towards it. Guys, am I audible?
Yeah, you are.
Yeah. Okay. Cool. I'll just go on. All right. So vector fields, on the other hand, are like vectors or a finite number of vectors. There's a vector at each point, and the smoothness of a vector field corresponds to the hereby it was not differing too much. I can, show this further, like right here. This is a scalar field, and it's a function of x and y right here. Like, there's an x graph and a y graph. Consider this a simple representation of a scalar field on a Euclidean space. After that, you have the representative vector field right here. You have arrows to point out, and also you have the scalar field depicted in contours where the arrows are pointing right up. So right here you can notice that the closer the contours are, the more the curve is going to be. You can represent this in multiple forms, and you can get like a scalar that's basically real numbers at every point and vectors that are arrows pointing. All right. So let me get to orientation, which is a little bit of a tricky one, because this paper presents this in a very abstract manner. But I will try to explain this as well as I can. Okay. So consider a single two-dimensional image in a Euclidean space. Like a Euclidean space R3, you have a two-dimensional object. If you can flip it about its surface and still not get its mirror image, then it is orientable. But if you flip it about and you get its mirror image, it is non-orientable. And an example of a non-orientable manifold would be a Mobius strip or a Klein bottle. So if I was to explain this in one way, Mobius strips have a boundary, but however, like an ant could travel. The classic rule of a Mobius strip. An ant could travel on a Mobius strip while traversing both the sides and returning to its same point without having crossed a single boundary. And a Klein bottle doesn't have any boundaries. It just fills in within itself around its, the walls of the entry point. Around the walls of the. If you're not sure what a Klein bottle is, you could always Google it and take a look. So right there, if you flip those two, like imagine rather than imagining flipping a Klein bottle, I'm presuming that not a lot of people know it. Imagine flipping a Mobius strip. You would obviously get the mirror image of it, and therefore it's not orientable. There are more examples of non-orientable images, such as non-orientable manifolds, such as Roman spheres and all that. But feel free to explore when we are done. Okay. So right here in this diagram, you have multiple ways of representing, orientations, which I'll get to in a while. The use of orientation it's important for integration in Stokes theorem, and orientation only affects the overall sign. But when you're adding forms, you need orientation to get stuff together. We'll see how we add forms, or rather concatenate them. The pictures are pretty, of course. Okay. So orientation on manifolds on an internal scale. We'll just look at internal for manifolds. There's also internal external orientation, but that's only for submanifolds. How we are going to look at now, we'll just look at manifolds before we get to submanifolds. All right. So right here, I showed you the images, and it's like for a zero-dimensional manifold, you have pluses or minuses, albeit conventionally you have to represent it as a plus. For a one-dimensional manifold, which is a curve or a line, you have arrows that point up or down. For a two-dimensional manifold, which has two-dimensional length and breadth, let's say, you have an arc which points in a clockwise or an anti-clockwise direction. Versus for a three-dimensional manifold, you would have a helix structure representing it. Like a right-handed manifold would go on the right way, and a left-handed manifold would go on the left way. Like you can see in this diagram, clockwise and anti-clockwise. You can see in this diagram that it keeps. You don't really need an arrow to represent this, and you could just look at it and infer that this is a way to represent a three-dimensional, orient a three-dimensional manifold. Okay. So right here, just like I said, you have a plus or minus. You conventionally have a plus. You have an arrow pointing one way or the other. You have arc pointing clockwise or anti-clockwise. On a three-dimensional manifold, you'll have a helix pointing one away or another. And just like I said earlier, you can observe that unlike in one-dimensional, two-dimensional cases, you don't need an arrow for helix. So next, we have orientation on submanifolds. Now, this is where it gets slightly interesting, because, like I said earlier, within a manifold, you have a submanifold. And since manifold, like submanifolds are just embedded manifolds, they can be orientable or non-orientable. With orientable manifolds, you notice that there's internal and external manifolds. Like for an internal manifold, it's pretty much the same, like orientation for a manifold. But with external, you would have something that's quite interesting. Like for internal manifold, you can just remember this, apply to the manifold within it. But if the manifold is external, let's say protruding out, we'll see some examples of it as we progress. I know it's a little abstract, but I would prefer if you guys like actually viewed this, sort of visualize it, which is why we have a lot of pictures right here. Because if this was just text, we'd be completely lost. Anyway, external orientations depend not just on the dimension of submanifold, but also the dimension of the embedding manifold. So, the manifold, submanifold, if the submanifold is external, it also depends on the dimension of the manifold that, bounds it. So, yeah, right here you have the table. So, wait. For a point, 0, 0, for a point within a point, you just have plus or minus. But, for a point within a line, which is the embedding dimension, right here is the manifold. Submanifold dimension is this submanifold, the external submanifold. Right here, you'd have the points that go up or go down. For a one-dimensional manifold and a one-dimensional, submanifold, you would have plus or minus, like so on and so forth. You can just combine both and take a look at it. I mean, you can take a look at this and have a look at it for like 30 seconds maybe. I'll just explain it to you meanwhile. So you have a submanifold, like a point right there. So this submanifold dimension is 0. So it's within the surface, and therefore it will have like the arc-like structure. And for a three-dimensional manifold, the point is within a three-dimensional for a point, or rather a zero-dimensional submanifold. There's a three-dimensional cube or spheroid or whatever you prefer as a three-dimensional manifold. That would have a helix-like structure with the dots, which will be following the orientation. And for one, like I already explained that earlier. So yeah. You have the embedding dimension right here is two-dimensional and one-dimensional line. So it's a line within a surface, and then a line within a three-dimensional figure, and another arc within a two-dimensional sphere manifold. Like right here, three-dimensional spheres and three-dimensional embedding dimensions and submanifold dimensions. You can visualize so on and so forth. I would not want to hinder that, so it's up to you to visualize. But right here, I would like to explain this because this seems quite obvious. So a three-dimensional manifold, a three-dimensional embedding manifold, and a submanifold dimension, is a two-dimensional line. So it's a surface that points out. Right here, you could probably visualize the thumb rule. That would be a classic example for this. And yeah, this could be electrons or anything as such. Subatomic particles within atoms and such. So internal and external, twisted and untwisted. Where do these merge together? You would call an internal orientation as untwisted and an external orientation as twisted. So right here you have a table which dictates whether these are definable and essential as such. And also if you have not figured out yet, vectors and forms also have orientations. So they may be twisted or untwisted, or they may also be internal and external. Like you can see this table right here. External, it would be twisted. Objects which can have orientations, and the correspondence between untwisted versus twisted, and internal versus external. Yeah. So yeah. Next, we'll view at concatenation of orientations. Okay, so what is concatenation? That's basically adding two things together. You can combine two orientations together. Like take this one where we, rather than me explaining the text and I'd rather have you visualize this. So yeah, right here you have a point which is dictated by a plus. The plus a line gives rise to is this 0 plus 1, so it should just result in 1. And this again 1 plus 0, which is still 0 again. But this is again 1 plus 1, which results in 2. So this gives you 2 dimensions. It's just basic addition math and whatever we learned right now. But you can visualize that and you'll get an idea of that. Well, this is around a surface. So this is 2 plus 1, which would give rise to 3, so on and so forth. So this is how you concatenate orientations, like combine 2 orientations together and get that. But also you can see that untwisted orientations
You're inaudible.
I'm audible now?
Yeah, you're audible now. Yeah.
Okay. My
Go ahead.
internet's glitching a little, so yeah. Sorry about that.
We all have bad internet. Go ahead.
Okay. Is it fine now?
Yeah, absolutely.
Okay. Cool. Right. Network seems to be too slow. Please stand by. Okay, wait. Give me 2 minutes. I'll just get back to. So yeah, where did you guys get cut off before I was doing it? Hello.
Yeah, you
Yeah,
got
the concatenation of
Yeah, concatenation. Okay, thankfully
Go ahead.
not too much is lost. Okay, so right here we have okay, my network seems to be a little slow. So yeah, wait. Give me 2 minutes. I'll be back. Okay, I hope that's better. Right. Okay, now I can present it to you. Okay, now I was at concatenation right there. And like I said, you can just visualize this. Like I said, like we said earlier, this paper is quite easy to understand. But before we dive into differential geometry, I would like to let you all know that whatever we are visualizing right now is not what it exactly is, because it goes a lot more deeper than that. Right here in this diagram, we can see curves created by pipe cleaners. Like the authors asked us to refer to some pipe cleaners. So a line that goes from X to Z to Y would create a helix. So it's just a combination of dimensions right there, and you concatenate and get stuff. That's about it. So yeah, there's just what I explained earlier, and much more in a little more scientific terms. But yeah, I'll get to inheritance of orientation by the boundary of a submanifold. So if a submanifold has a internal orientation and a boundary, let's just say I'm not quite sure about what I can give as. Let's just say a circle, for instance, within a sphere, or a sphere within a sphere. And a sphere doesn't exactly have a boundary, so it's not exactly a good example. But yeah, you can imagine any or let's just say like a circle right there. If it has a boundary, then the boundary also inherits the internal orientation. So right here we can see those examples of that. And if it's an external manifold, it's going to have it inherits the external orientation, because right here you can see orientation of a one-dimensional manifold. It has pluses and minuses, and goes it follows the same convention. It just obtains that from the manifold it's within. So yeah, the boundary of a two-dimensional manifold, again, like you can notice the boundary also in the arc, like anti-clockwise arc is going in. And the boundary of a three-dimensional manifold, of course, you have a sphere right here, and it is following the same helix rotation of the three-dimensional ball. For an external one right here, you can notice how this follows more of a helix structure, just revolves around and catches on. So yeah, that's one. This again an external one where you have it pointing out, and the boundary is also going in an anti-clockwise direction. This is going in the anti-clockwise direction again, like towards the right. So this also follows the same way. And the boundary of a three-dimensional manifold right there, you have it pointing inside, like the charge is the plus is within. It's the external orientation of the three-dimensional ball right here. The external orientation is three-dimensional ball, and the arrow is pointing inwards the external orientation of the two-dimensional sphere, which is within. So yeah, orientation of vectors. So we know, like I said earlier, vectors and forms can also have their own, orientations. So yeah, they can have internal untwisted orientations, and there's another type of vector called twisted vectors right here, and they're also called axial or pseudo vectors. An example of this is a vector such as magnetic field B. So right here you have twisting and untwisting vectors. So yeah, but rather this is more of a reference to twisting and untwisting. So yeah, I'll just stick away from that. They look like external orientations of one-dimensional manifolds as depicted in table 1, which is right here, which follows the same convention, but just apply that to a vector rather than us applying that to a manifold. So twisting and untwisting, this will be what I cover last. If a manifold has an orientation, we can use it to change the type of orientation of a submanifold. So if like a manifold has let's just say the embedding orientation is this, we can use it to change the submanifold's external orientation. So that twists it. For instance, we can also convert an internal orientation into an external orientation. So yeah, there's convertibility right here, twisting and untwisting. That's exactly what this is about. The convention we use here is to say that if we concatenate the external orientation first, followed by the internal orientation, one must arrive at the orientation of the manifold, like right here. So you could notice that if you take the internal one, it would be like this, and the external one, it would be like that. So looking at these examples and visualizing would help you understand what this is. Starting with the untwisted form and then twisting and then untwisting, it does not change the orientation. So, twisting and then untwisting just gets it back to the normal state. But, if it's twisted and untwisted, it will probably have a different one right there. So you can notice right here how it happens. So that's about, for my part. If you guys have any doubts, you could ask away. Guys?
Okay, so I think it would be appropriate if we hold the question session at the end.
That's right.
Yeah, so I think we have a time constraint as well. Right?
Yeah. True.
So
yeah, go ahead. I'll give you the floor to Rishi.
Okay, so I see you did a lot of highlighting. Okay. So I'm just going to start off by summing up what Sundaram said. So what is a manifold is the first question. So this is a basic paper, so I'd like to stick to the basic definition. A manifold is just an object, right? So let's take this sphere or a ball, and that's called a manifold. And what's a submanifold? As the name suggests, it's a manifold within a manifold, right? So then twisting and untwisting, let's just take it as, to give the manifold an orientation, right? So then to say, okay, fine, it's going in this direction, or you're supposed to look at the ball in this direction, because you could look at it from anywhere, right? So then to give it some sort of, let's say, a perception or a rotation or something like that, we use twisting and untwisting. But then do make a note that even untwisted manifolds are essentially twisted or have an orientation, but they're of an external type. And internal twisted manifolds are ones with what we call as twisted manifolds. So I'll be moving on to the differential part of the differential geometry. So far all we've heard was just geometry, right? Just balls and shapes within the ball and stuff like that. So then we'll see where the part differential comes from that. So what are closed forms, right? Whoops, the internet's being a bit wonky here. Let's just forget this page for a moment, right? So then what are forms? So by definition, forms are actually multilinear functions or maps, right? Which takes a vector and outputs a number or a real number, right? And as we saw in this paper, right? So we don't want any math in it. So I'd like to make an apology that, let's remove that definition of that calling a form a multilinear function, right? But instead, what we can look at forms are as objects or tools that we use in differential geometry to perform calculus and other operations on these shapes, or what we call manifolds, right? Since if you notice till now, we haven't talked anything about a coordinate system, right? Either a polar coordinate or like a Euclidean coordinates. We've never mentioned any of that because we can see that manifolds are independent of coordinates, right? It's what coordinate system that we choose that the manifold obtains. Okay, so when an object doesn't have a coordinate system, right? How would you perform calculus? How would you find the derivative at one point of the manifold or the integral around that manifold, right? So there is a small question there, and that is where the word forms come in, right? So right now I'd like to make you think that forms are integrals. Okay, so then let me just scroll down, just skip all of that, it's useless. Okay, so let's take forms as integrals. Okay, so what's a zero form, or like we call them as zero forms or top forms, right? So zero forms are essentially just scalar values, right? They're constants in a field, such as we saw before a scalar field, right? And then we move on one dimensional more. So what is a one form? So many of you already probably know the answer. A one form is an integral, right? One form is a line integral. So it's an integration in one dimension. So essentially, like if you see, there's a red line there. So we take an integral on that red line. So a one form is essentially a line integral, right? So we can extrapolate that knowledge onto two forms as being surface integrals and three forms being volume integrals, right? So I'd like to make another small point here. Again, I'm defeating the purpose of the paper, but for those who are interested, right, a more rigorous definition that we can take for forms are that we can define them as covectors, right? So you can look this up and maybe, take this as a starting point for doing actual differential geometry. But again, talking more on, covectors and tensors will provide a gateway to flood this lecture with mathematics, which I don't want to do. You don't want to hear me do that. So now let me straight away start with the operations that we perform on manifolds, right? On forms, right? So let's take this diagram here. Is my cursor smooth, or am I like moving all around the place? So okay, so I assume that my cursor is quite cohesive. Hello?
Yeah, I think so.
Yeah, you can hear me, right? Thank you. So I was pretty stuck there, right? So okay, so let's take this example, right? So this is a one form, right? So how I would like you to visualize this is you see these lines here, right? Let me just use this to just look cool. So then you can take this as a field, right? So this is essentially just like this, right? It's just going in this direction, right? It's going right. Okay. And then the blue line is the same. It's just going this way, right? So that's pretty simple. So what happens when you add both of these forms? It's simple. So there are fields that are going this way and there are fields that are going that way. So then you just add them and then there you got a field that's going this way, right? So these are untwisted one forms as if they have external rotation, external orientation, right? But then you see here we have twisted one forms which have internal orientation, right? As we see, it's pretty visual here. We have an internally oriented one form, right? So this takes up a different addition law, right? So then this line goes this way, this line goes this way, and then you get a one form going this way, right? So then only the orientation changes, right? So then let's just talk about multiplication of vectors and formed by scalar fields. So if you study 10th grade physics, you would obviously know what happens when you multiply a scalar with a vector field. It's simple. The vector gets multiplied by the scalar quantity, right? And the same thing, what it's analogous. So a scalar you multiply it by a vector field you multiply it by a scalar field, right? So then we have already talked about addition of forms, and then I'd like to talk to you about the wedge product, right? So what is the wedge product, right? So then we talked about forms as integrals, right? So then if we take this diagram here, right? This diagram here, yes. So then essentially what all these confusing diagrams are saying are, so you take two one forms, right? So then they're one-dimensional line integrals. And then you perform an operation called the wedge product, right? So what the wedge product does, it essentially forms, let's say, again, I'm heavily visualizing here. Don't take my word for it. It's not mathematically correct, right? So then you can perceive the wedge product between two line integrals as it forms a rectangle, right? And then you get the surface integral, right? So then you get a two form. And then so what happens when you multiply a two form and a two form together? It's simple, you get a three form, right? So then now we finished up with all of that. Now yes, we're going to look at integration, right? Now this is where the differential and the calculus part of the entire talk comes in, right? So then let's see this, right? This sphere, right? What we're essentially doing here is we're just passing a field, right? A twisted one form field inside a sphere, right? So then essentially what these lines are integrals. So when we pass, let's say 1, 2, 3, 4 lines in here, so there are three lines that are going up, and so there's one line going down. So let's take the integral of this to be 3, right? I'm just making a basic assumption here, right? But then what we do see is we only get the value 3 if we assume that the form is non-closed or they have a boundary. But then what we're talking about here is a specific form called closed forms. Yes. What are closed forms? So a closed form is essentially an integral which has no boundary or something that closes in on itself. So this is a one form, right? And this is a closed one form. Yes. And then you see these ones, they don't seem to close in on them. So how can we look at this? Right? So we can just imagine this to be a huge and infinitely large circle, right? That ultimately closes in on itself. So I think that is pretty clear. So I'll move on to, oops, it's raining heavily here. So that conservation, okay. If I have some breaks in between or like some crackling voice, please do feel free to tell me to stop, right? So 4.5 conservation laws, right? So simple, what are conservation laws? Some conservation laws that we know are, conservation law of thermodynamics, right? Conservation laws of energy and conservation of current and all of that, right? So then how does differential calculus come in there? So conservation laws state that, hello? Okay, so my voice is breaking?
No, it's clear only.
It was,
Yeah.
but it's fine now.
Okay. No problem. That's what, okay, hello? Yeah. So what are conservation laws, right? So, can you just give me a minute? My car seems to be getting flooded. I'll just come in a few seconds. Just Okay, so I'm sorry that those are just some problems you need to face when you're in the wilderness, right? So, okay, can we continue? Google? Hello? I'm audible, right?
Yeah, but your voice is a little breaking a little.
Okay, don't
Your
worry.
voice is a
No, my
little
voice.
robotic, but that's fine.
No, my voice was actually cracking. I'm sorry. Like, it's cold outside. So, okay, so we were looking at conservation laws, right? So then, what are conservation laws? Conservation laws just simply state that the integral of a closed form is zero, right? So there are three conditions which essentially puts this into place. So the submanifold of dimension p must be the boundary of another submanifold of dimension p plus 1. So what essentially says is that, so let's take, you have a circle inside a circle, right? So then the submanifold inside, right? So then the smaller circle, the smaller sphere inside is essentially a smaller part of that bigger circle and essentially has a boundary inside that sphere, right? So that's essentially that simple. So the p plus 1 dimensional manifold must not go to infinity. So then the submanifold shouldn't just extend to infinity, because as we saw, closed forms need to close in on themselves, right? So then when there are just line integrals which extend to infinity but ultimately close in on themselves, when we have a manifold that extends to infinity, we see that that doesn't apply here, right? It, right? Or to say that the closed form is, well, the integral of a closed form is zero.
One second,
Hello?
Rishi. Like
Rishi,
you got cut off in
trailed
between.
off.
Yeah.
You trailed
Yeah,
off.
like we weren't able to hear what you were saying.
Okay, so where did I tail off?
When you explained about conservation, like right when you got to the next page, I would say.
Okay, so I was just talking about this, right? So I didn't say anything much. So I was just saying that, you need to make sure that the integral of a closed form is zero, right? That's the only thing you need to know, right? So then let's
Right,
take
that's true.
let's take this annulus here, right? It has a hole, right? So another thing I mentioned was that a manifold, there are no laws that states that manifolds themselves shouldn't have any holes, right? But then our conservation law states that whenever we integrate, if we integrate over a hole, the integral is non-zero, right? And when an integral is non-zero, the form isn't closed, right? So we have an annulus here, right? So let us visualize this, right? What do they mean by all these lines and gibberish, right? So this line here, this is a form, right? This is a one form, right? This is a closed one form because we see that it goes around and closes in on itself, right? So when we take the path of integration to be this, right? So we integrate over this place, right? So when we integrate over this blue line, we can obviously see that we don't pass any holes, right? There are no holes in this part of the manifold. So we can ensure that the integral is zero, right? Because it closes in on itself. But then when we take this green path of integration, we can see that we pass through a hole, or we have a hole inside, right? So it's intuitive why we can see that the integral is non-zero, right? So if you did basic calculus, you'll probably understand what that means. So yes. So yes, I'll just mention about what the DRAM cohomology is. So the DRAM cohomology is, if you want to just visualize it, it's pretty hard, or you don't want to visualize that, or what this is entirely useful in is in the actual mathematical part, right, of differential geometry. But then we don't want to look at the math, so I'll probably skip on it, but then I'll just give you a gist on what that is. So we saw that the integral, for the integral to be zero, the manifold should not have any holes, right? So then when you cannot visualize, right? So right now we can see, there's a big hole in the torus, right? when we take complex manifolds or like something much more non-visual, we don't know exactly whether we are integrating it over a hole or we're just integrating it without holes, right? So then the DRAM cohomology essentially provides the framework to make sure that wherever we are integrating it, right, it has no holes, right? So that's essentially. So 4 dimensions is, I'll just leave that off because that defeats the purpose of the entire paper, because we cannot visualize 4 dimensions, right? We've heard examples of, X, Y, Z, and T. When even that time dimension, we can't physically just visualize it. So I'll skip over that. And this is pretty simple. Am I not scrolling now? Non-closed forms, right? So non-closed forms are the exact opposite of closed forms, right? They have an integral value, right? So let us take this simple example here. Oops, I'm scrolling all over the place. I'm sorry. So these lines are non-closed one forms, right? So then if we do basic addition, right? Remember, what is integration? We just, we use the Riemann sum, and then we just add up the individual part, and then we just try to find out the area of any given shape. So then let's take this square, right? Or this place. So then when we move in this direction, right, we can see that we only have one form passing off. It's pretty confusing. So then the value of integral here is 1. Okay. Then if we take the opposite path here, I'm just going to skip the counting because we don't have much time. So we can see that 1, 2, 3, 4, 5, 6 something. So we can see that the value of the integral changes on the path taken, right? So then these, while non-closed forms are called forms submanifolds, right? Because when any line closes in on itself, we get a shape, right? But then these non-closed forms do not close in on themselves. So we do not have a shape, right? So this is all just, it's not needed. Yes, Stokes theorem. One thing while I was reading this paper, the Stokes theorem is very, very important in differential geometry. It essentially states that the integral of a curl of any object is equal to the exterior differential of the one form surrounding that manifold, right? But then we don't need that again, because that's going to defeat the purpose. So what are differential exterior operators? Yes. So I forgot to mention what this is. This is pretty simple. So let's take a shape, right? Let's take a ball or the scalar field as we saw before, right? What the exterior differential operator does is it essentially finds the derivative or the gradient of every point around that shape, right? And then outputs let's say a scalar field, or let's say, wait, let me go back to that image long back. Essentially just outputs an image like this, right? So then it essentially gets a gradient of every point around that manifold and returns its value, right? So scrolling down. Am I audible?
Yeah.
I sound like one of these professors on Zoom class, I'm like, are you audible? Am I audible? Then it's all bad. It's all bad internet, right? Yeah. So then, okay, other operations with scalars and vectors. I'll finish this up very quickly. So combining one form and a vector field to give a scalar field. So again, so let's take this example, right? So then we have a one form, right? That's line, and then the one form is, let's say, going this way, right? So then this is very simple. We just combine untwisted one form, right, and an untwisted vector field, a vector field that's going this way. And what we do is we just count the number of lines that this vector passes through. So that's 1, 2, 3, 4, and 5. Right, but then we see here that it's -5, right? Why is it -5? Simple, because it's oriented to the left, right? So the next one is vectors acting on a scalar field. A vector acting on a scalar field gives a new scalar field. It's not needed. And then
Hey,
this,
Rishi wants it. Okay.
yeah.
Okay. Yeah, like
What's
how
up?
is it oriented to the?
See, right? See, we said that. See, if it's untwisted, right, it doesn't mean that it isn't oriented, right? So an untwisted one form is essentially an exterior oriented one form, right? So then we see that the orientation isn't like this, right? So the orientation is this way, right? So see, again, we are trying to visualize this. If we want to take this mathematically,
Okay.
we take this as a covector and a vector, and then we multiply it, and then that outputs a scalar, right?
Mm-hmm.
And then again, to visualize it, I said it in that way. But then if you want mathematical rigor, you could refer to the
Okay.
textbooks, right? So
Okay.
internal contractions, again, this is another simple concept only, okay? So then let's take this line here, right? It's untwisted 2 form, right? And then this vector, blue. So essentially, visually, what is happening here is, so we are just extending this way, right? So like we are providing infinite lines, and so that produces this green, what's it? One form, untwisted one form, right? So then we see, as Sundaram was talking about, was the concatenation of orientations, right? So then this is going this way, so and the vector is going this. So essentially, it becomes like this, right? So far all the simple stuff is over. So I'm gonna be handing over the harder bits and the metric and all of that, and how all of this connects to Maxwellian electrodynamics. Over to Pugal. Pugal. Nope, you're not audible, man. Not yet. You are not audible. Again, if you have any questions, we will be hosting a question session at the end. So feel free to ask. Yeah, you're audible now.
All right, perfect. Let me
Yep, go ahead.
Yep. So, I mean, there's nothing really difficult about what I'm about to say. In fact, I would argue that we've all seen just everything that I'm about to explain to you in Chinmaya's lectures. Right? So, we're just going to be looking at what we've already seen, but in a more rigorous formalism from all the stuff that we've learned. Right? So, as Sundaram said earlier, the metric is perhaps one of the most important objects in differential geometry. It's basically an object that allows you to compute the length of something. And we've already seen the metric. For example, in Minkowskian Minkowski space, we had the n mu nu term. This is basically the Minkowski metric, right? But in general, like Chinmay had mentioned earlier, we refer to metrics as g mu nu in physics. We use mu and nu because we're usually dealing with 4 dimensions, 3 dimensions of space and 1 dimension of time, and we use Greek letters, so that's the convention. And if you want to take up a naive case of how a metric is basically just a matrix that allows us to compute the length and the angle between two things. And I'll show you a very toy example of how it's sort of defined. So G mu nu, if we take it as just 2 dimensions, you can define it to be the dot product of the basis vectors E mu and E nu, right? So this could be the x, this could be I hat in Cartesian terms, and this could be j hat in Cartesian terms. So your Euclidean metric would look, okay, I'm just trying to find the white space, would look something like I hat, j hat, and this would be j hat, I hat, and then this would be j hat, j hat. So in a sense, you know that they are mutually perpendicular. So, you know, the dot product would be 0, and it would just essentially be 1. So this is what the metric for Euclidean 2-dimensional space is. A 3-dimensional space, it's just another one in the diagonal, and we'll see more examples. But the essence is that the metric can be defined this way in a very limited sense. And this is probably the first equation. I am going to be throwing more at you because I think right now we've got a visual idea of things, and we're sort of ready to build ahead of what we've already learned from special relativity and the parts of this lecture. right? So how can a metric let you compute angles? Well, it's pretty simple. You have the dot product here, and the dot product is basically just the magnitude of mu times magnitude of nu times the cosine of the angle between them, right? And that's pretty much it. You just have to sort of move terms, and you can then get the angle between them. And there's another interesting thing. Well, it can tell you the distance between 2 points, but it does so by something known as a geodesic. Very weird term, very interesting term. Let's keep this geodesic in mind for what we're about to see next. Because if you want to know the distance between 2 points, it's basically the length along the geodesic between them, right? Let's just keep that in our head for a second. Also, there's a very fancy statement here. It enables you to convert into vectors one forms and vectors into one forms. It's called the metric dual. It's a really, really, really fancy way of saying I can basically raise or lower. I'm not going to write lower because it's a larger word. You can basically raise or lower indices, right? That's what we've been doing all along in special relativity. But here's the thing. Your raised index and your lower index, although they appear like, okay, I'm turning a column matrix into a row matrix or a row matrix into a column matrix, although it's so simple, you have to understand that the row matrix and the column matrix actually are very, I'm sorry. Mukul, you have a question?
No.
Okay, sorry.
No, he was just unmuted. Go ahead.
Okay.
Oh, yeah, I misclicked on such.
Yeah, no issues. So they fundamentally live in two different spaces. So usually you call the space where the vectors live a vector space, and you call the space where its dual components lie the dual space. All right. To put it in a very naive sense, your column vectors live in vector space, and your row vectors live in a dual space. Well, that's a very naive way of looking at it, because your dual space has a set of 5 rules. Otherwise, you can't call something a dual space or a covector space. And you can't call something a vector space without a few set of properties. Right? So this is just something that I want to hint upon right now. And also you can convert P forms into N minus P forms. We'll look at this later as well. It's called the Hodge dual. Well, if you want me to expand upon what a P form is, well, as Rishi mentioned earlier, your 2 form, which is also called a bilinear form, is just a very fancy way of saying, hey, I'm taking a vector, I'm taking a covector, or I'm taking a row matrix and a column matrix, and I'm going to give you a real number. All right, that's a very fancy way of saying that. A P form is a very, very fancy way of saying there's a function that takes in P number of vectors. There are VP number of vectors. All right, and it's going to give me a real number. And what the P form essentially does is it allows us to generalize ideas of volume and area to n dimensions. So if you have V vectors over a manifold that has n dimensions, all right, so you have Pn basis vectors. So you can just take the P form of it, and that would give you a real number, and that would basically be the n volume. So n volume is basically a fancy way of saying, okay, if I have 2 dimensions, it's area, and then if I have 3 dimensions, it's volume. So yeah, so we're just slowly adding some rigor into what we've just got to. And of course, we've seen the issue of signature in the Minkowski matrix or the Minkowski metric. Yeah, minus plus 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 as the signatures, where minus basically stands for the time dimension. But also there's an equivalence here. You can also alternatively, as Chinmaya suggested in the lecture earlier, you can also use plus minus minus. And the reason you can use 2 different metrics is we as physicists only give a shit, or only care about these properties. So we care about this property, which is to say, if I multiply the metric by the Lorentz transformation, I must, in the special way, I must get the metric back. And if I multiply, let's say, any position vector, or as they say, 4 vector, all right, if I Lorentz transform it, and if I again multiply it by a covector, which is basically I'm trying to find the space-time interval to say if I apply the Lorentz transform to the space-time interval, there's going to be no change. So these are the only two things that we care about. That's why we have two different metrics. And Chinmay also did go into it for a bit. You can refer to his lecture if you'd like to know more about it. Or we'll also be exploring it in the upcoming set of talks as well. Well, let's get down to business, which is how do we represent a manifold? I'm sorry, a metric, and how do we represent it in space-time? All right, or in Minkowski space. Right. So this is how you would represent a metric. So how would I calculate the length of a vector? I would just look at the number of lines it's passing through. So this is it's a rather very visual representation of a metric. Again, not all metrics have to look like this. Not all metrics are like this. But this is a way of thinking of things. Another way of thinking of it would be just to think of, the lines of a grid in a graph sheet is basically, that's a metric, right? So again, we fundamentally care about special relativity here, and as a consequence, general relativity. So I'll get right to the point. So we had actually explored special relativity in 2+1 dimensions, which is to say 2 dimensions of space, 1 dimension of time. So this is a very terribly drawn light cone. You can see this is a light cone. Yeah. Oh God, why did I draw it? So yeah. Well, there are 3 ways of classifying vectors. And it all depends on this light cone. So I'll just zoom in. So if my vector lies on this, it's called a light-like vector. If it lies in here, it's space-like. If it lies outside it, it's called time-like. That is to say, if I calculate the length here, it will be larger than 0. If I calculate the length here, right along this edge, and there is a reason this edge is very important, because in Minkowski space, we have a convention of representing the line that makes a 45-degree to all the time-like. Yes.
Hello.
Yes.
Yeah, Pugal, you kind of broke away in the middle, I think.
Whoops.
Yeah.
Where did I break away? Oopsies.
I don't know, like I
You were
thought my
explaining
internet
the stuff
was
on the
bad.
light cone.
I was explaining this stuff on my phone.
Yeah.
Okay, was I here? Where did I go? Where did I?
Yeah.
Yeah,
go
you
away?
kind of left where you were waving your mouse there, yeah. Go ahead.
Yeah, okay, so very quickly to brief on that, if your point lies inside the light cone, you have a space-time interval larger than 0. If it lies right on the edge, it's called light-like, and it has an interval of 0. And if it lies outside, it has an interval less than 0. And you can pretty much just take any 4 vector, multiply it by just do the math of shoving in the metric, and you can see that if you really want your space-time interval to be less than 0, you'll end up outside the light cone, and so on. But again, the representation wildly differs, and that's exactly why you have 3 different diagrams. Before we go there, this is probably a more naive example to look at. If you want to look at unit spheres on flat space, you can see that they're sort of all uniform, right? Their volume isn't distorted, their area isn't distorted, and so on. But if you look at curve space, things are going to look a little more messier, a little more stretched out, a little more distorted. So let's just keep that in mind. And the reason we have three different representations of the metric, of the same metric in Minkowski space, is because these three vectors act in completely different ways. Well, to start off, time-like vectors, well, okay, they represent the velocity of massive particles, is what the author is saying. I can't vouch for it. I've not studied it, but they point to one of the two components always. So in a sense, you can distinguish between future pointing time-like vectors and past pointing time-like vectors. So you'd essentially use the metric in as two sheets. One as an upper hyperboloid and one as a lower one, as shown in this diagram. And whoops. All right. So outside the light cone is space-like, not time-like. I am sorry. Yes. And space-like means Chinmay was just pointing out to me. Space-like basically means they're not causally connected. And in fact, if you look at the last Friday talk, we talked about Bell's version of causality, which is to say, if your two light cones are excluded in space-time, if you have two light cones right next to each other, which are non-intersecting, that's the only way you can say that this event in the future wasn't caused by this event in the past. And there's a fundamental limit in electromagnetism, and that is that all changes can only propagate at the top speed they can propagate is at the speed of light. So if there's a vector that lies outside it, that just means it isn't going to cause any change. It's not going to cause anything that lies inside the light cone. Chinmaya, I hope I'm getting that right. You can pitch in wherever you can. Your mic is unmuted, so you're more than welcome to. Okay, yes. And what you can do with light-like vectors, which is to say that they lie right on the border, is, well, again, you can distinguish between future and past, and that's exactly how sort of causality propagates. And for time-like vectors, again, I'm sorry, for space-like vectors, they're not the four velocity of anything because they lie outside the light cone, and that's kind of not that's kind of illegal because that's the speed at which causation can occur, right? So you cannot exactly distinguish between space-like vectors. And that's essentially because they do not obey the laws of causality that electromagnetism sort of imposes on us, or what special relativity imposes on us. Right. And like I said earlier, just the length of a vector, it's basically like counting the number of grid lines on your graph sheet. If you just draw a line, you want to find out what's the length. You can use Pythagoras' theorem, and then you can just count the number of boxes it crosses and then find it out. But again, the Pythagorean theorem doesn't have to hold everywhere. It only holds in Euclidean space. It just may not hold in all spaces. Right. So well, this is yet another representation. Well, I'm not really going to go into detail here, but you're more than free to look at it. It's basically just a superposition of all these three onto a two-dimensional graph, 1 + 1 dimensions, essentially. Right. So we've been dealing with a lot of spaces. So as usual, we'll just use a bit of etymology. Orthogonal means perpendicular. If you're given a vector, then the metric can actually be used to specify all the directions that are perpendicular to it. So you can sort of collect these vectors. You can sort of collect them at a point, and you can sort of form a plane around them, and this plane is called the orthogonal subspace. So if you have a vector, this is your metric, and using this you can find out what's orthogonal to the vector, and you can thus create a plane out of it, right? Yeah, and this is pretty much the same thing but in space-time. So your hyperboloid is used to specify the metric, and if this is a vector, your metric can tell you what's perpendicular, and out of that you can form a plane. Well, again, for the two-dimensional case, find angles. You can just look at this, and we know what the dot product formula is, and it's essentially a very naive calculation. But there's a more interesting angle to what it means in Minkowski space. And what it means is usually the cosine lies between -1 and 1, but in Minkowski space, it can sort of go above 1. And this is what we call the gamma factor, which is basically a very fancy way of denoting the Lorentz transform, which is basically the 1 by square root of 1 minus b squared for the one-dimensional case, right? And we've all seen this, and it's quite closely related to the angles, because if you, I can't remember exactly, but there was this set of notes that Chimia sent over, and there was a way of representing a Lorentz matrix as a form of a hyperbolic rotation matrix itself. So yeah, so you can use the Lorentz matrix or just the metric itself, sort of compute gamma factors and angles. Well, you can also use a metric to define magnitudes of forms. That is, when I say forms, I mean functions in a sense. So if you were to measure the magnitude of a one form, which you can sort of think of as grid lines passing over, so what you could then think of is, how do I specify the magnitude of these grid lines, or how do I specify the magnitude of this covector or one form? Well, all you need to do is just count the number of grid lines that this is cutting through, this object is cutting through, and you just need to divide that by 2. So if this is an n-dimensional manifold that I have on my one form, all I need to do is do a simple calculation of n minus 1 by 2. And that will essentially give my magnitude. And again, it sort of varies the higher up as you go. If you want to measure the magnitude of a 2 form, then that would mean you just place an n-dimensional manifold on the 2 form, and you do n minus 2 by pi, you'll get the magnitude. So again, you have more and more formulas, but let's not go into that. Let's not get lost there. Right. So the metric, again, like I mentioned earlier, can be used to convert a vector to a covector, or one form, and a one form to a vector. And this is just, again, a fancy way of saying I can raise or lower my indices by multiplying it by the matrix. So I hope you guys remember this. X mu the twistedness, as we saw earlier, is invariant under this index lowering and raising. For space-like vectors, the orientation again is also preserved, and for time-like vectors is also the same case. And a very interesting instance for light-like vectors, well, you just the covector for light-like vectors is always perpendicular to the vector itself, and don't know why this is true, but it's an interesting property. Yep, and this is a very visual way of looking at things. So if I have a space-like vector, the orientation doesn't change. Well, for a time-like vector, it's reversed, and for a light-like vector, it's always going to be just perpendicular. Okay, so I mentioned this really weird name that's called a Hodge dual. Let me just try to review it for you guys. Well, it gives you, it's basically a function. It's much similar to your covector. Oops. It takes in a p form which is a function that takes p number of vectors. Okay, I'm just going to keep going. I'm going to keep going. If I'll end up with my pth vector, and it takes me to my real line. So this is what you guys should think of when I say p form. Well, it takes a p form and it gives a unique n-1, n-p form, where n is the dimension of the manifold on which you have the p form. And another thing is, it gives you this n-p form such that it is orthogonal or perpendicular to it. Well, obviously, the twistedness is changed, and if one starts, and another important property of Riemannian geometry, I think, which we'll explore later on when we're doing GR and so on, is if you start with an untwisted p form, you take the Hodge dual of it, you'll end up with a n-p form with pretty much the same orientation. And there are a few properties, but you wouldn't really require them much to go forward. The measure from a metric, again, it's a concept that's given very little space, so I wouldn't rather delve into it. Right. So what is a smooth map? It's just a function that maps one manifold to another. And excuse me, the simplest case, Chinmaya had also mentioned it earlier, is what is called a diffeomorphism. And whenever you see a fancy term, the first step is to break it down. So you see two words here. You see diffeo and you see morphism. So, well, I really don't know what diffeo means, but whenever I see morphism, I know it's a map or it's a function where one particular structure or many particular structures are preserved. All right. So you see morphism. I want you guys to think something's being preserved. We got to find out what it is. Right. So in the case of a diffeomorphism, it's what you call a one-to-one function or one-to-one correspondence between your points in the manifold and the target manifold. So a one-to-one map is essentially, wrong pen, is to say that if I have these points on my manifold and this is on my target manifold, if I have these points such that I'm basically doing a one-to-one map. So yeah, so due to this one-to-one map property, you have a lot of corollaries, and what happens is that they must have the same dimension, and in a few senses, they must look the same, right? So, but however, when you include, if this manifold has a particular metric and this one has a different metric, obviously they will be looking different. So a smooth map is in a sense that you can, it's a map that you can use to talk between two different metrics as well. For example, if you map in, let's take optics as an example. If you map between one manifold where there's light rays that travel in straight lines, and in another, you can sort of think of it as light traveling with a hidden object. So it's sort of like looking at a torch that is being shined underwater. You can look at it from the outside, it's going to be diffracted, but if you look at it from the inside, it's going to look different, to be dispersed. So yeah, well, we've actually encountered smooth maps before, and it's precisely in the embedding of submanifolds. And in this case, we're basically mapping each point in a lower manifold. So you have a lower manifold and you have a embedding manifold. So I'm just going to map from here to here, right? So what this means is every point in this, well, in that case, every point in the embedding manifold, embedded manifold, it usually corresponds to a unique point here because it's a one-to-one map. But what happens is you can still have some regions that are not being mapped at all in the embedding manifold. So yeah. And another way, and another map is what is called a projection map, which is basically the opposite of this. And this is a good example of a projection map. What I'm doing is I'm taking a three-dimensional manifold. These are two lines in my 3D manifold, and I'm sort of projecting them onto a sheet of paper or a 2D manifold. So a way of looking at this is if you've ever gone to those puppetry shows where they sort of just shine light and they move puppets, but then you only get to see the projection on the screen, which is visible to the audience. You don't get to see the puppets that are moving. So, yeah. Well, after this discussion, it's quite natural to move into what is called pullbacks. Well, a pullback is basically, again, a pullback is also a map, but it's a very particular type of map. A pullback basically means if I have two manifolds, manifold A, manifold B, I'm basically going to map all of my covectors here to this map. That's exactly what a pullback is, right? Obviously, we'll limit ourselves to diffeomorphisms here, but this is essentially the crux of what a pullback in the context of differential geometry is. When you hear pullback, I want you to think a map between covectors, right? So what essentially happens here is pullbacks, they preserve the degree of form, they preserve the twistedness of a form. But however, like obviously, when you're transforming between two manifolds, there is a little deformation going on, right? So in Chinmaya's lecture, he talked a little bit about what topology is, and for a topologist, a torus and a okay, this is a very bad representation of a coffee mug. Trust me, I do have good coffee mugs, but yeah, are pretty much the same object because they just have one hole. So how does this morphing happen? What morphs? Well, that's a rather tough question, and unless the metric is defined, because if you can't define angles, if you can't define lengths, it's kind of senseless to talk about the difference between a torus and a coffee mug, because essentially they look the same because they have the same number of holes, right? So, well, for if you can take pullbacks of p forms as this title suggests, and if you take the pullback with respect to an embedding manifold, that is, if you take this map of an embedding manifold here, if I'm trying to take the covectors, what exactly happens is you end up with an intersection of the particular submanifold with the form manifolds that Rishi was speaking about. And again, if you're pullback a p form in an m-dimensional manifold, to an n-dimensional manifold, you basically end up with a p-form submanifolds which have m minus p dimensions because the intersection of these m minus p dimension form submanifolds with these other n minus p manifolds, well, they'll correspond exactly to what a p-form is. And your p-form is basically just, as Rishi mentioned earlier, you're taking a vector, you're taking a covector, you're taking multiple vectors, and you just want to get to a real number. So these images will give us a good picture of what it means. So projection mapping is just as we saw earlier, and if you take the pullback with respect to a 2D manifold, which is the red plane, embedding onto a 3D manifold, well, you have an untwisted 2 form, which is the blue curves here. You will actually end up with a twisted 2 form. I'm sorry, you'll end up with an untwisted 2 form, which is the green dot. If you project this line on this 3D object here, you'll end up with a dot. Yeah. And there are a few more examples given here. If you pull back with respect to a 2D thing, again, it's all about intersections and it's all about what's perpendicular to what. Yep. So you can definitely apply pullbacks to metrics. So what does it mean to pull back a metric? Well, when you pull back a metric, when you basically say I'm going to go from because a metric in a sense, in a very loose sense, is a type of P form. I'm basically saying I want to go from one manifold to another for this particular metric. You'll obviously end up with a different metric, which is with respect to the second manifold, and this is called a induced metric. And for example, if you have a tori which is embedded into flat 3D space, you get something that is shown in figure 61. So yeah, so if you try to pull back this onto flat, you'll basically end up with circles, basically projecting these spheres onto this flat manifold. And we use a different term when it comes to transforming vectors, and that word is called push forward. And it's again a very fancy way of describing a function. Well, it's just the word is just fancy, but the function is very simple. So if I have a manifold here, and if I have a vector, a bunch of vectors here, what it means is if I'm doing this push forward operation, it basically means I'm having a vector in manifold A, I'm having a vector in manifold B, and I'm going to take the tangent of this vector and I'm going to map it to this tangent here. So it's basically a map between tangent spaces. So you can sort of think of it as TA going to TB, right? Well, of course, it's a little weird because obviously sometimes one particular tangent can correspond to multiple tangents here. It isn't exactly a one-to-one map. So you could say that sometimes push forwards aren't diffeomorphisms, because a diffeomorphism in a strict sense has to be a one-to-one map, right? And sometimes it may not even obviously it does not result in a vector field, and that's precisely because some have no vectors associated with them. Some can just be tangents with no vectors, or some can just have multiple points associated. So there's a little bit of vagueness surrounding this. And armed with this understanding, I'm just trying to be dramatic, you can quickly sort of slide into electromagnetism. But before that, let's just look at push forward of a vector, and this is exactly what I mean. So if I want to map the tangent vectors, I'm basically mapping this tangent to this tangent, of this tangent to this tangent. So yeah, so this is exactly what is called a push forward operation. And armed with this, we'll step into electromagnetism, and we will use electromagnetism as a very exploratory way of sort of visualizing everything that we've discussed so far. We're just trying to put it all together and look at things. Right. So the basic elements of electromagnetism are Maxwell's equations, and they are described using 4 vector fields. You have E, B, D, and H, and there's this relation between D and E, and then B and H. So these are what you called permeability and permittivity. They, in a sense, describe the medium, and they are constants essentially. And the reason they are constants is because, well, you want your the way light behaves is the propagation of frequencies. The radiation of different frequencies, they do travel at the same speed. So that's exactly why this is a constant and not a variable. Right. So whenever you think D and E, see D and E, you can sort of keep this notation in mind. And a very naive example would be if we didn't have this property of these permeability and permittivity being constants, you wouldn't have rainbows. So yeah, you wouldn't have all light rays sort of dispersing equally. Each frequency would disperse in different fashions. So, yeah. But again, there is a degree of complexity when it comes to Maxwell's equations. The reason is because they are linear equations. So they, in a sense, even if you take up any electromagnetism textbook, you're looking at toy models most of the time. So sometimes electromagnetic phenomena can be quote unquote nonlinear, or sometimes they can break down or behave differently, at Planck length. So again, you can take Maxwell's equations in a sense to be an effective field theory of electromagnetic phenomena, right? And again, you've got a few more things in Maxwell's equations. You have rho and you have J. So your rho and J give rise to your charge and your magnetic field, essentially, right? And obviously, when we were looking at four vectors, if you guys remember, when Chinmay was speaking, what's the first component of a momentum four vector? I'm just asking. Guys, is anyone here?
It's the energy. You are hearing
Exactly.
me?
Yeah, I can hear you. Exactly. So similarly, you have a four vector J nu, all right? And the first component of this J nu is actually just rho. All right. So I'm just trying to build a level of similarity. And again, you sort of can do the same four vector logic, and you can rename, you can combine this. And the notation we use here is this weird H to denote this J nu. This J nu is basically a combination of rho and J. And I'm sorry, this weird J, yes. But usually, most places you see it as J nu. So whenever you see nu or mu, instead of mu, you should think, okay, four components. That's it. And let me just write down Maxwell's equations for a bit here. And obviously, we'll start with electrostatics and magnetostatics. And Gauss's law basically states that the divergence of the electric field is basically divergence of D is given by rho, or this in an alternate notation, as we saw earlier, is basically divergence of E is equal to rho by epsilon naught, right? So what this and there are a few more laws. So you have the curl of E is 0, which means it's curl free. What does it mean for something to be curl free? Well, there's a special word for this. It's called solenoidal. And well, actually, I think this should be B. It shouldn't be E. There's a mistake in the paper. So B is actually curl free. So B curl free basically means if I have a magnet north or south, field lines are going to look like this. My curl always, my divergence always measures my net outward flux. That's as divergence as an operator in vector calculus means what's my net outward flux. So your divergence can be negative or positive. Negative means there's inward flux. Positive means there's outward flux, right? So if you just take so when I say, and curl basically measures, with respect to a perpendicular vector.
1 second, but shouldn't it be like the gradient of the magnetic field should be 0?
Oh, oops. Yeah, sorry.
Yeah,
Divergence of
divergence.
I am sorry. The divergence. Wow, it's just been one semester. The divergence of B is 0, which basically means there's no net outward flux of this magnetic field. Whatever happens, all the lines that come from the north just end up in the south. And for E, it's curlless. So yeah, and in the language of forms, we can sort of rewrite these vector calculus equations. So that's what we're going to do with all of these knowledge of forms, duals, and metrics. We're just going to sort of change the language in which we're speaking. So obviously, the visual way of looking at this for Gauss's law, first things first, nabla dot E is equal to rho by epsilon naught. The positive charge is given by a twisted three form, which is the dot here, and this twisted three form's magnitude is given by rho, which is the charge density. Charge density basically means net charge by volume, right? And this is also okay. So I can look at this to cause these field lines, or I can consider the field lines themselves to be fundamental, which is what we're doing with considering this three form rho as the twisted two form of these black lines. Twisted two form, as in more visual sense. Again, whenever I say two forms or one forms, think grid lines, really weird grid lines that can be spaced out or spaced in. And in a vacuum or similar constructions, you have a correspondence between the D and E. So this is to say that the D is basically the Hodge dual. This field lines are basically the Hodge dual of the rho that is causing these field lines. So you have two different pictures for just one electrostatic situation that's going on here. And you can do something similar with magnetic fields. If your magnetic two form B, this is B, this line is my two form B, are unbroken curves, which basically means they extend. They're basically non-compact, to say that this is the manifold in which B lies in. B is going from one end to the other end of a manifold. There's no boundary to it. And if this is unbroken, to the non-divergence, which basically means it has orientation, and yet again it has external orientation, which is given by green, which is lines that you'll always see associated with your magnetic field B, and your red. Okay, yeah. So your okay, we'll dive into this. So yeah, we just reviewed this. Yep. So again, there's yet another correspondence here. Two different pictures. You can look at the orientation, or you can look at the field lines themselves. Well, this is due to the fact that for example, if you throw an electron in the magnetic field, it's only going to change its direction, right? That comes from the Lorentz force law. Well, again, two different pictures, and they are both sort of Hodge duals of each other. This can you can apply this to Ampere's law, which I think it makes it more obvious. So this is my line of constant current, and if I have a constant current, the twisted this is a twisted J form. Twisted two form J, and you can sort of think of this line to be the derivative of this H form. That is to say that, okay, if I have this H form that intersects with this line, I can then take the derivative, and I can arrive at this twisted two form. And again, there's a Hodge dual correspondence between these two. So similar case for the permanent magnet. Your blue curves and are basically twisted one forms, and your ellipsoids, these really weird ellipsoids, are generated by the permanent magnet, and you can see that they are actually perpendicular. The field lines are actually perpendicular to the B fields. Thus, obviously, you can then say that they coincide, that these field lines intersect with this. And this is again due to a really weird phenomena that happens in permanent magnet, where the closer you approach the poles, weirder your field gets, your field lines get. And yeah, so these are electrostatic examples, but what happens for electrodynamics where my charges can move? Well, then we're just going to head to space-time. And you're going to see some really weird thing that's going on here. We're actually trying to represent the entire space-time here. So that would mean you have 3 dimensions of space in 1 dimension of time. So for starters, we can start with the conservation of electric charge. So what does it mean for electric charge to be conserved in space-time? So that means you have a twisted 3-form J that can be interpreted as particles, as charged particles, and they're basically spread out all over space-time. And in a sense, if you choose the metric correctly, these lines are just going to be straight lines. And as we've seen in even a naive space-time diagram, you have a straight line going, you have a straight line going through space-time. That basically means the object is stationary. So in a sense, you could say that, okay, your charges do not change over time. But obviously, your individual charges can change over time, whereas the net charge remains the same. So your conservation of charge is basically a very complex way of saying, if I take the time derivative of the sum of all charges, I'll get 0. Basically means no change in time. But of course, this is a consequence of Maxwell's laws, and it's a consequence of very ideal cases. This doesn't happen all the time. I mean, yeah, just look at your batteries. Next, what we could go to is conservation of magnetic flux. So, well, what happens here is so initially we thought of charges as lines in spacetime, but if your charges were allowed to dynamically move, then what happens when a charge moves? You end up with a magnetic field B around it, which is denoted by this maroon arrow here, and essentially that creates a field that is perpendicular to this, right? And the influence of this field is what is denoted by this blue slice. Say it encodes both of those fields, and then since we're in 4 dimensions, they form they loop outside and they create these 2-dimensional submanifolds, right? So this is basically trying to so this was something that we also looked at. So you can look at the mu nu. This is my f mu nu, right? This square is containing my f mu nu, and you can then say that with respect to time, with respect to x mu, this basically just, if I just differentiate this, if I take one particular slice of this, and if I want to look at the change of it, I'm basically going to just end up with how my charge changes. So I'll end up with this. So this is a very fancy notation to denote 2 of the Maxwell equations that encode E and B. Well, you wouldn't just need to consider normal fields. You can also consider excited fields, right? So your excited fields basically encode the permittivity of the medium as well. So why do we call it excited? Is basically it tells you exactly how excited, or most of the time how non-excited light rays or electromagnetic radiation is as it passes through a particular object with a set of properties. So yeah, and this is basically us showing the Maxwell's equations that contain D and H, and D and H are basically E and B along with your permittivity and permeability. Well, we've talked about these 2 things separately, and you can combine them through the Lorentz force law. Well, the easiest way of saying things is to say that, okay, these things are actually perpendicular submanifolds in 4 dimensions. They have the same orientation, right? And this is just a visual representation of F is equal to QE cross B cross plus B cross B, right? So that's basically the Lorentz force law. And again, it's quite easy to see the math. Like because you have the cross product for V and B, so which means your magnitude increases as the more perpendicular these 2 submanifolds are. and they are in general perpendicular and depending on the media or the velocity of propagation varies. What you can do then is just take a singular particle, which is represented by this line, this world line, green world line, and well, your Lorentz force is basically just going to be your straight arrow red, and it's orthogonal to the form F near you, the tensor that we talked about earlier. So and moving forward, this will definitely be very useful with GR. And on that note, I'd like to conclude the talk. And if you could just excuse me for 2 minutes, I'll be back and I'll be ready to field questions. I just to get some water. Thank you, guys.
Okay, so anybody has any questions? You
Yeah,
can
if
shoot.